Good. All right. Now, you would think we'd be done with solids and liquids, but we're not. All right. We're going to talk about the change between them, between a solid, a liquid, and a gas. That's what we're going to spend the rest of our time on, something called dynamic equilibrium. You see, I've already told you about crystals and everything I wanted to tell you about the kinetic theory and description of solids, and everything I wanted to tell you about the kinetic theory description of liquids, all right, and the properties and all that stuff. There's not much of a test here. It's like about 3 days of notes and 1 lab is all we had. So the rest of our time is going to be spent on their interchange between them, and that's where things get tough. This will not be as easy as what we've been doing. Now, the funny thing is, this is one of those times, I don't say this very often, that even if you study, you can do poorly on it, okay? Usually I'll say, like, well, these are math problems. You don't need to study. You'll do fine on them if you understand them. You do well on the review. So don't even bother studying. Other times I'll say, well, there's a lot of memorization of this, definitions and multiple choice. You're going to have to study. But it's rare that I say that this is something that even if you study, you may not be able to apply it well because it's not something you can just memorize. This is not a memorized kind of thing. And most of you guys are very good at memorization. You wouldn't be in this class, the honors class, if you weren't. All right, you're all very good at memorization, but this is application, okay? Now, what is dynamic equilibrium? Well, this is an equilibrium. Take a look at my little balance here, okay? You see where this is balanced kind of in the middle, all right? And that's an equilibrium, but it's not a dynamic equilibrium. So to illustrate a dynamic equilibrium, I'm going to tell you a little story, which is a good time of the year to tell this story because potholes are all over the place, right? Spring's coming, although you'd never know it by looking outside. And although at least we get the big storm. And with spring comes potholes and birds. But potholes are the things we don't want to hit with our car. Well, we don't want to hit birds either way. So let's just say, that, again, keeping in mind this equilibrium, because this is what I'm going to get back to in a second. Let's say we got PennDOT working on the roads. Okay, they're especially going to do that road between Delos and my house because it's ridiculous. The one that goes behind the factories there, it's just potholes everywhere. Anyway. So I got a crew out there. They got 2 crews, actually, and there's a pile of bricks on one side of the road, and there's a pile of bricks on the other side of the road. Now, the one foreman says to his guy, hey, you know what? It's silly having 2 piles of bricks. He says, Stan, I want you to take all these bricks over to the other side. Meanwhile, unbeknownst to him, the foreman on the opposite side says, you know, it's silly having 2 piles of bricks. Stosh, why don't you take all these bricks over to the other side? So all day long, 8 hours, Stosh, except for, breaks, coffee breaks, and, lunch. Stosh and Stan walk back and forth. They pick up 2 bricks apiece. They walk all day long. How you doing, Stosh? Good. How you doing, Stan? How's the wife and kids? And if they walk at the same pace and pick up the same number of bricks each time, what's going to happen to those 2 piles? They're going to stay the same. But they didn't really stay the same because each time he picked up different bricks. That is dynamic equilibrium. You see, this is static. Nobody's going back and forth between. Those 2 piles are staying the same. These marbles are staying the same. Put that light on so you can see a little bit better. These marbles are staying the same. What I'm saying in a dynamic equilibrium, which happens in both chemistry, in the chemical equations, and in physical changes like solids to liquids to gases, which we're going to talk about, you got Stosh and Stan going this way and that way, carrying their bricks, okay? And yet you have no change because they're happening at the same rate, okay? They're happening at the same rate. So that you do maintain an equilibrium. So that is dynamic equilibrium. You got 2 guys running between, think of it that way. 2 opposing forces happening at the same time and at the same rate. Get that light off again? That's the definition of dynamic equilibrium. State in which 2 opposing forces occur simultaneously at the same rate. Now, just like in regular static equilibrium, the result is the same. You don't have a net change, but there's constant change, and that is very important, right? There's no net change, but there is constant change. Hence the word dynamic. Dynamic does not mean what you think of when you think of like Batman and Robin and a dynamic duo or a dynamic personality. Dynamic simply means to be moving or changing. That's what the word means, a dynamo. All right. So a guy who has no net change but is constantly changing, that's what we're talking about here with a dynamic equilibrium. Your bodies maintain an equilibrium. Not the same exact way, but similar. What do we call it when your bodies maintain the same Stasis.
Homeostasis.
Homeostasis, right. Okay. See, stasis means the same in body, and being homeo, right? Being. So, basically, it's called homeostasis for biological organisms, and your bodies do this all the time. You have to maintain a very specific temperature, pH, water amount, okay, interstitial fluids, and oxygen levels. Okay, all these things have to be maintained in your body. If you're off by just a little bit, you feel terrible. Think about your temperature. 98.6 is normal. 101 is just a few degrees above that. And if you have 101 fever, you're down in bed and feel like you're going to die and probably having hallucinations. Okay? And that's just a couple of degrees, 3 degrees off of what your normal temperature is. You guys maintain this, not through exactly the same way, but through lots of chemical equations, chemical reactions that are equilibrium problems, that's how you're able to maintain all that. Anyway, there are two kinds of dynamic equilibrium we're going to talk about. The first one, chemical equilibrium, and I'm going to have to move these out of the way so the people at home can see us.
Hi, Mom.
Chemical equilibrium is a topic for Chem 2 because it is, as I told you a minute ago, this topic, this concept, it's so deceptively simple. It's going to seem like, well, okay, there's nothing to that. It's going to seem that way for two reasons. We're going to be dealing sometimes with very familiar stuff that y'all know the answer to. And other times, it's going to seem that way because it just seems like, well, it's just one sentence. I mean, I just got to apply that one sentence. How hard can it be? And that's what it's going to come down to eventually, one sentence. But trust me, when you get to apply it to chemistry, it's going to be a lot worse. All right? For example, I've been lying to you. I've been lying to you. Not really lying. I've been implying something. Chemical equilibrium is what exists between reactants and products in the chemical equation. Do not copy this down. Normally, we've been doing equations like this. This has probably been my first equation that I wrote from back in chapter 1 or 2. I first started talking about salt. Okay, and we learned over the years how to predict that it was going to form that, what kind of reaction, composition, decomposition, replacement, exchange, how to write the formulas with the charges from the periodic table, how to balance the equation with a 2 and a 2, how to do stoichiometry with it, all that stuff. I never found it necessary to tell you something. Most equations aren't like that. Most equations don't just go one way. They go both ways. So that while you're coming together with Na and Cl2, NaCl is breaking up into that at the same time. Now, that's not the case for the ones I gave you. This does go to completion. It is one way. Many of them that we did, all the ones we did in lab were like that. If you burned magnesium, you went from magnesium plus oxygen to magnesium oxide. All right? But what I'm saying is in reality, in life, especially in human beings, especially in organisms, they go both ways. Most of the reactions go both ways. That can get to be a problem. Gets to be a problem with all that you learned about stoichiometry and everything else that you learned. Really, most of the stuff you have to make adjustments for, it's not what you think. I've been giving you, a simplified version. So we are going to save chemical equilibrium for Chem 2. It's a much tougher topic. We spend 3 full chapters on it because it involves chemical reactions and calculations with those chemical reactions, actual numbers. We will not be doing numbers with physical changes of solids and liquids and vapors today, but we will when we get to Chem 2. So chemical reactions between reactants and products, that's a topic for Chem 2. We're going to let that go. Now, as far as this, what we're concerned is phase equilibrium. The equilibrium that exists between solids and liquids and vapors, because those are the 3 phases of matter. And I basically have 3 possibilities. First things first, though. I cannot have a phase equilibrium unless I have a closed container.
Sodium.
So, yeah. Sodium thiosulfate. Is that all you need?
Yeah.
Oh, okay. I thought you said sodium.
No. Sodium.
Thiosulfate. Is that enough?
It should be. I'm just doing the seating.
Okay, yeah, we just saw that the other day. All right. Okay, so it has to occur in a closed container. All right? Like your hamper is a closed container. Closed in the hamper. Closed. Not clothes. That would be closed. Closed container. All right, it has to occur in a closed container. Otherwise, well, you'll see why as I go through the examples. Let's look at a couple of possibilities. There's actually 3 possibilities. First possibility is Emily wakes up and takes notes. Second possibility, I walk over there and hit her in the head. Which possibility do you think is going to happen, Emily? Right.
Well,
They exist between the solid, the liquid, and the gas phase. And there are 3 possibilities. Now, for each of these, I am going to, and this board here is all about just getting the basic terminology down so you understand what I'm talking about. The next board is going to start to stretch your ability to apply it. This will be just about what our terms are when we talk about phase equilibrium. I'm going to have to move this out of the way while we're doing that, or we're not going to have any room. All right. So I can have an equilibrium that will be set up in a closed container that's between a liquid and a vapor. I put a lid on a container, like this one here, and after I put an airtight lid there, it will evaporate a little bit, then it will stop, not stop evaporating, but it will reach an equilibrium with the amount of condensation. We'll talk about that in a little bit. It will reach an equilibrium. For a liquid-vapor equilibrium, the equilibrium exists between 2 processes. What's the name of those 2 processes? Going from a liquid to a vapor or a vapor to a liquid, what do we call them? Evaporation and condensation, exactly. So the rates of evaporation and condensation for this guy are going to be equal. Now, I am going to show you this information in multiple ways. You've already seen one way. I'm going to use that balance and these marbles to illustrate an equilibrium. But I also use another way. I talked about Stosh and Stan, my PennDOT workers, my ubiquitous PennDOT workers. I'm also going to use an equation. I want you to write this equation down. Liquid is going to become a vapor. Now, in order for a liquid to become a vapor, what do we usually have to add to it? Yeah, energy, right. So write this equation down underneath. Liquid, you add energy to him, he becomes a vapor. I'm going to look at it in terms of an equation because that's going to help me a lot when it comes to applying what's called the Chateliers principle. What do we call the forward direction? Going from a liquid to a vapor? Evaporation. And what do we call the reverse direction? Condensation. So write that little equation down. Now you're going to write an equation for each of the phase equilibriums I'm going to set up here, as well as a few little notes too. Remember, this is all about just getting down the basics, the terminology, you understand. All right. A solid to a liquid, you're talking about what 2 processes here? Melting, and what's the opposite of melting?
Freezing.
Freezing, sure. The rates of melting and the rates of freezing are the same at equilibrium. Can we write an equation for that guy? I hope so. What would it look like, probably?
It's going to look like...
Solid will be on one side, right? And liquid on the other, and what will be in between? Energy. And the equations, or the arrows, mean in the forward direction what? Melting, a simple word. And the reverse? Freezing or fusion. But we'll use freezing, simple enough. We'll talk about heat of fusion in a little bit. All right. Pretty simple. Not doing anything, like I said, challenging your intellect yet. I'm about to when I get done with this board. All right, let's do the last one, because this one at least has some new terms that you're not familiar with. Going from a solid to a vapor is also possible. Those of you who were here the day before Friday, we did that iodine little demo. Remember? The purple haze? Remember that?
Mm-hmm.
And if you were here on Friday, you saw the results of that sitting on this table right up here. All right, little stalactites hanging down from the top of the evaporating dish. Or actually, it was from the watch glass. Now, when it goes from a solid to a vapor, do you guys know what those words are called? Going from a solid to a vapor directly? Sublimation, right. But the other one you're not so familiar with. It's called deposition. Okay, so the rates of sublimation and deposition are equal in this case. Now, I've run out of room on the bottom of my thing, so I'm going to write the equation for this guy up here, if that's okay with you people.
No.
Even if it's not. Check it out. Here we'd have a solid plus energy yielding a vapor, where the forward direction is sublimation, and the reverse would be deposition. Okay, so solid plus energy yields vapor. I mean, it's just like the other ones before. The top one is going to be sublimation, where you're going forward, and deposition going backward. Simple enough. And by the way, iodine is not the only thing that supplies. What's another classic thing that goes directly from a solid to a vapor without becoming a liquid? Now, well, water can do it, yeah. I told you about that. When you open the freezer on a hot day, you see steam come out. There's no liquid water in the freezer. Obviously, that's sublimation as well. But the one that's very common, that makes fog for fog machines. Dry ice, yeah. If I ever get any dry ice, every now and then I do get some. Do you get any in your bakery at all? Dry ice? No. You have to get it for, you'll use it to send stuff through the mail if they want to keep it cold. There's other medical companies will ship things in dry ice as well. Well, anyway, if I get any, I'll show it to you. It's little demos I can do with that. So, all right, good enough. So there's your three things. Nothing. I said, well, you said it's going to be hard. Nothing hard here. We've heard of all these things before. Yeah, except for this. We are now going to talk about how we can make changes to these equilibriums and how we do make changes. And I have a neat little demo I'm going to do here. I'm going to go back to this, talk about a lot of different ways here. The principle I'm going to try to apply is LeChatelier's principle. Now, Mr. Krupp is your principle. LeChatelier had a principle too. Different kind of principle though, right? How is it spelled? P-A-L, right? For Mr. Krupp, because the principle is your pal. Okay.
Everyone laughed at the camera.
Laugh for the camera, please. Thank you. I gotta put the applause. Oh, wait, I gotta put the applause.
Oh, you're just funny.
That's what I'm gonna get. I'm gonna get an applause sign. You know, just put applause, like you're blinking in between, or laughter. They do that, you know. On
throw tomatoes at you.
There's not gonna be a tomato sign. Just saying.
I'm thinking there is.
All right. There it is. That's all of it. That one sentence, that deceptively simple, elegant statement is so difficult to apply. If a stress is applied to a system in equilibrium, the system acts to relieve that stress. This is one of those things that I'm always, as a teacher, you eventually get to the point where you're not shocked by it. But in the beginning, my first 5 or 10 years of teaching, I used to be like, why don't they get this? What is so hard about this? I'll go over it and over it and over it, and I'll give you thousands of examples. And over the years, I've added tons and tons of different ways I'm going to show it to you. And yet, people will have trouble applying that simple. The rest of this week, pretty much, well, maybe the next 3 days, pretty much, is going to be spent applying that simple principle to different changes in phases. Now, it's not hard to apply that to your bodies. If you get hot, you have to maintain equilibrium. So what do? You sweat to keep your temperature down, right? If you get cold, what do? You shiver. You get hungry, you eat. You get thirsty, you drink. You drink too much, you pee.
Too much, you juice.
I don't think that's quite how it works, but okay. I would like to use this tape, but anyway. So you guys are used to seeing this with your bodies. Your bodies do maintain this equilibrium. We call it homeostasis. But you're doing it through a very complex process. I mean, your bodies don't just automatically do these things. You have lots and lots of buffer systems in your body that allow you to maintain the same pH and that maintain everything about your bodies being the same. What I'm saying to you about LeChatelier's principle, I can apply this to chemical reactions and physical changes like phase changes. And that's exactly how it applies. It does the opposite of whatever you're trying to stress it with. Okay? Now, oops, I'm out of let me tell you how I can stress it. I already mentioned one of the same stresses your body has is a stress that you would have for a system at equilibrium, like phase changes. And that would be temperature. If you heat up your body, you basically have to adjust to that. And if I heat up a chemical reaction, that's equilibrium, or if I heat up a physical change, a phase change, that's an equilibrium, I will get an effect. I will change that system. It will try to get back to being at equilibrium, especially if it's in a closed container. So let's take a look at this. Let's draw in terms of an equation first. And you'll see why in a little bit. There's that same equation we saw a little while ago for a liquid-vapor equilibrium. Let me ask you this. Which process, evaporation, that forward direction, or condensation, the reverse direction, would be favored? Which is it going to do more if I increase the temperature? I doubt I'll get the wrong answer for this. If everybody agree, if I heat up that system, it will favor evaporation, right? Okay. Let me show you something here. I have a little demo I'm going to show you here. All right. And now, because here's the thing, I'm going to have to tell you why it does this. Now, the demo I'm going to do is going to involve a paper cup filled with water and caught on fire. That's right. Turn that light on for me for a second. We like on. Okay. We like fire. Fire is good. Fire bad. All right. Let's see this. Okay, there we are. There we have it. Let's light this guy up. I know some of you are saying to yourself, "Whoa, wait a minute! What are you doing? What is that paper? What's that cup made out of?" Paper. Turn the light off. You can probably see it a little bit better even here. Both of them off. Yeah. Mm-hmm. That's fire. That's paper. Like paper and fire. That's actually a song. John Cougar? Anyway, no, probably not. Look at that. Well, what's not happening? It's not catching on fire. All right. You can put the lights back on. Both of them. All right. And there's a reason for that. It's not the obvious reason that you might think. All right. Paper is flammable. I didn't cheat there. It really is. But right now, I am stressing that system. It's actually technically not an equilibrium because it's not a closed container, but the same basic thing applies. I'm stressing the system. I'm adding energy to it. And I want to explain to you exactly what's going on here because there's a reason. This should have gotten a higher temperature than it is. But I've got all that water in here, and that water is going to be doing something. I'm favoring evaporation, like you said. Look what happens up here. When water evaporates, what does it take with it? Energy. It takes energy with it, enough energy at least to keep this guy from catching on fire. All right? You know how much I'm going to heat this? Is there a limit? Not really. I'm going to heat this guy up until he's boiling. I'm going to actually boil the water. I guess that's as good as it goes. Actually boil the water. I'll show you the water boiling in a second. It's almost there now. But it all has to do with, you can copy this down while you're waiting for this to boil. It all has to do with the fact that the evaporation process is actually sucking energy with it, taking energy with it, so that the paper does not catch on fire yet, until all the water is gone. I'll copy that. That's almost boiling already. And I'm going to pick up my camera and show the folks at home. There's nobody absent today, is there? No, there's no folks at home. There will be next year. You know, I'm going to use the same video next year. Wait, there it is. Can you see that? Can you see that, folks at home? That water is boiling, or at least very close to being boiling. Wait, there you go. You see that? Yep, it's boiling. Put it back down here. It'll boil out of the cup even. Now, just waiting for it to boil a little bit more. That's a Dixie cup. Now, notice I did not use a waxed one. Why not? Yeah, the wax would have melted and burned. Don't want to do that. and then probably leak the water all over the place. All right. I know you guys back there can't see it boiling, but couldn't see it boiling, but you can in a second.
I like how it's burning on top.
Yeah, where there's no water. See, look at, see it boiling over? Whee, whee. Okay, now I'll turn this off. Turn the lights off again. Pour this out. Very, very hot water. But you know, once the water's gone, and I do the same thing I was just doing, that ain't gonna last very long. Yeah, I'm afraid not. Yep, fire.
Oh
Yeah, it looks like marshmallows. Yeah. Okay. You can turn it off. Oh, all gone. Okay. All right. Okay. Nobody to give any shout outs to, unfortunately, today.
Give a shout out to Marie, even though she's not here.
Marie, you just saw the same thing.
Doesn't matter.
She's good. Well, that's going too
Shout
far.
out to Delos Baker.
Buy your pizza at Delos.
She eats your cheese.
Emily only eats half the cheese. Ask for extra cheese.
Oh my god, I'm running to calf.
Where you going? No. Emily, sit.
I can't go to get a calf.
You cannot go to the cafe. No. We're in the middle of class. Sit. Why do you have to go to the cafe?
So much food.
I just wanted food. I'm dying.
Eat in lunch period.
I do.
All right. Look at it. Now, this is the most important part. You definitely don't want to miss this. Now, watch. Now, I'm bringing this back for a reason. All right, this is the most important part. Now, most of you guys, look up here. Emma, you need to pay attention. This is absolutely imperative. Because what's going to happen right now is I'm going to explain to you why this happened. Up until now, I think everybody would have probably predicted that if I heat up water, it's going to boil. And if I cool it down, if I have one up here, it's going to freeze. Here's the problem. Life's not always going to be that easy. I'm going to talk about, well, actually, later today, in a few minutes, and you're going to have to do in a worksheet by the second half of the period in a little bit, pressure changes, volume changes, and you're going to have to predict what's going to happen there. And those you're not so familiar with. So you have to understand why. Now, I'm going to go back to this equation and explain to you why. Watch this. The reason this guy went forward, let's talk about LeChatelier's principle. What did I do to this system? Which of those three things did I directly affect immediately by putting that on a flame? Energy. Everybody agrees. I added more energy. Basically, what I did, let me take a couple out of here and a couple out of here and just show you. Basically, what I did was, this guy's hanging out, he's in balance. And I added stuff to the left side. I made this side too heavy. Well, this little balance has no choice. He can't go anywhere. He can't do anything about it. But if I've got Stosh and Stan running back and forth, and they want to get it back to equilibrium, who's going to have to work faster? Stan is going to have to work faster. Assuming Stan is a guy going this way, right? He's going to have to go faster until he comes back to being at equilibrium. I'm going to have to favor the evaporation process to bring him back to equilibrium. That's why it evaporates faster. That's why it eventually boils, because of that. And vice versa. Take a look. If I were to remove energy from this guy, decrease the temperature. Yeah, I got to take these off of here so you can see. If I were to decrease the temperature, which direction would be favored? Well, I think everybody, again, knows. No one's going to get wrong that if I cool down vapor, it's going to condense. But now you'll know why. Can someone someone who can apply LeChatelier's principle, this statement, say why it is that I'm going to favor the reverse direction? What did I do to this system when I decrease the temperature?
You're condensing all the energy.
I'm not condensing all the energy. That does not make any sense. You're mixing your metaphors there. What did I do? In terms of these three guys, in terms of this scale, what side did I make too heavy or too light? Think. I decreased. I removed energy. It's like this. It was happy, it was balanced, and I stuck my hand in there and I took out some marbles. Now, what's happened? That side's too heavy. Who's got to work faster now? Stosh. He's got to get his butt in gear. Not Josh, Stosh. Stosh and Stan. Until they get back to equilibrium. So, write this down. this is going to favor the reverse direction. Okay? So now you've seen this in terms of basic notes. In terms of an equation. In terms of an explanation of a principle. In terms of an analogy to Stosh and Stan, our PennDOT workers. In terms of a little demonstration you just saw with me boiling water in a paper cup that didn't catch on fire. I got one more way I'm going to show it to you. All right? One more way I'm going to show it to you right now. Okay? And I want you to draw these for me in your notes. You're going to actually draw 3 pictures. The last way it's going to make sense to you, I hope. All right? Is everybody okay with this? Oh, here, let me apply this. Here's where I'm going to kind of hint ahead a little bit to Chem 2. And I'm also going to hint ahead to tomorrow's class, too. I don't care what these things are. Look here, don't do this. A plus B yields C. Here's what LeChatelier's principle comes down to. What way would be favored, forward or reverse, if I added more A? Everybody agree it would be forward? We try to get rid of that A. What way would be favored if I added more C? Reverse. Which way would be favored if I removed B?
Now you broke it.
Reverse.
Reverse, because it's going to try to replace it. Which way would be favored if I remove C? Forward. That's what LeChatelier's principle comes down to in a nutshell. But the crazy part is, you got to apply that to, I mean, it wasn't so hard with temperature. We all knew what was going to happen anyway. If we heat up water, it's going to boil. If we cool it down, it condenses. And it won't be that hard if I talk about a solid going to a liquid. If I heat up a solid, which way is it going to go? It's going to melt, right? If I cool down a liquid, what's it going to do? It's going to freeze, right? So we know those. But there's a reason for it in terms of LeChatelier's principle. You understand? Now, that's the last way I'm going to show this to you. And remember, there's so many different ways, and I added a lot of these over the years, and I realized how people had so much trouble with this. Okay, watch. This last way I'm going to show it to you is going to be pictures. I want you to draw a jar that has water on the bottom, a lid on the top. He's at equilibrium. You're going to draw 3 jars total. Okay? You're going to draw 3 total jars. After you draw that first one, I'll explain to you what you're seeing, what you're looking at. Draw this jar. It's got water on the bottom. By the way, this is an animated GIF I made myself. That's right. You guys all think you're so good with computers. You're so smart with your smartphones. You make an animated GIF like that.
I don't have this with things.
She doesn't.
There actually is a website you could do this if you ever wanted to make one. You may have done it with like pictures of your own. You could make like morph your picture into something else. You could have like a little short video almost of you they could post on a web page because they don't take up as much space. If you put a real video up, it takes up a lot of space. So GIFs are like a little bit smaller. Anyway, let's take a look at this animated GIF and talk about what's going on. Y'all have it copied yet? As I'm giving you my background. I want you to draw in this first one for the dots. Okay? You draw like maybe 10 dots and so in there. You draw about 10. The reason I'm saying I have a specific number is that you're going to, over time, they're going to change. You're going to see in a little bit. There's your initial situation. I put a jar of water. Right? A lid on a jar of water. It's sitting there. It's hanging out. There he is, right there. There's that jar of water. And if I just let it sit, over time, the rate of evaporation will be equal to the rate of condensation. It just sets up its normal equilibrium. Some are still evaporating, people, notice. Some are still condensing. But the net change is 0. You're not really getting any more or any less liquid or any more or any less vapor. Now I come along and I increase the temperature. Now, I want you to, by the way, you're going to have the picture here so you know. 1 picture, 2 pictures, 3 pictures with the stuff in between. That's what you're going to end up having is 3 total pictures, okay? So I hope you have enough room there. I probably should have told you that before you wrote your first one down. Would have helped. So you're going to have 3 total pictures. Here's your next picture, okay? What's going to happen to this jar what's going to happen to this equation, the same equation here? It's going to favor the forward. You all agree? We just did that. We just did that a minute ago. You all agree it's going to favor evaporation if I increase the temperature? Did I not just prove that by boiling water or in talking about it in terms of the equation a minute ago, right? Everybody's good with that. So what will this guy look like over here? Now, before you start copying it, let me say what it should look like over here. This is the second of the 3 pictures you're going to see. I'm going to have more evaporation, so I'm going to draw the arrow for this guy a little bit larger. Okay? And more water molecules are going to be becoming vapor. So you notice I've got more of them in the vapor phase here, and they're moving around fast. You can't show how fast they're moving on your paper, but you have more in the vapor phase. So maybe now you've got 15 or even 20, or 15, let's just say, dots. You have more dots, however many vapor molecules you want to show, because that's what those dots correspond to, water vapor or liquid vapor. But the big deal here is evaporation is greater than condensation. Do you see it? And you know why now. You know why it was favored. Right? Okay. Everybody go with that? All right. There's a crazy part to this now. Here comes the crazy part. If I asked any one of you, looking at this jar a minute ago, what would happen if I increase the temperature? Everyone, I would hope, after my previous board, would have said it's going to favor evaporation. It was going to evaporate more, right? How many of you would have said, eventually it'll be condensing more as well after I heat it up? Not many, but it does. And here's why. It's a closed container. Do not copy this next picture down. Don't copy this. I want you to just watch. Since I've got more evaporation, guess what? I got more guys in the vapor phase, which means there's a greater chance of them banging into the liquid and becoming a liquid. So this condensation starts creeping up because I've got more and more in the vapor phase, more chance of them hitting into the liquid phase, until eventually it reestablishes an equilibrium with a higher rate of evaporation and a higher rate of condensation. Yes, there are a lot more vapor molecules now and less in the liquid phase. That's your third picture right here. It reestablished equilibrium right there. Do not copy this. This is kind of an in-between transition.
What do we put in the middle?
Nothing. That's just over time. Eventually it reestablishes equilibrium. So if you had an arrow going between each of these, it would have been, that's your step one to the next one to that one there.
So
there's no explanation. It's just over time, that's what would happen just by virtue of the fact that I've got more evaporation, I have more in the vapor phase. And then I have more in the condensing too. So you see, it's not so easy maybe. The kind of questions I can ask can get really tricky. I could ask you a question like, at equilibrium, after I increase the temperature, what will the rate of condensation be, greater or less than it was before? And the answer would be greater, which doesn't seem to make any sense. Rate of evaporation, it makes sense that it would be. And we've only started to talk about temperature. That's the crazy part. All right?
How many dots in the last one?
Well, I would put maybe 20 by the time I get to the last one. So you're showing that you've got more in the vapor phase. All right? All right. Now, I'm going to give you one more thing. You have to go back. This is the previous board here. One more way I'm going to talk about this is something that is analogous to your own life, or not applicable to your own life. Last way, and then I'll stop the thing for a minute and give you a little bit of a break while and I'm going to undo the volume and pressure in a little bit. All right, watch this. Knowing how this works explains some stuff that you probably didn't realize it explains from before. Why does sweating cool you off?
Water effect.
That's the answer. But you need more of an explanation for that, but that's the answer. A lot of people think, well, sweat cools you off because your skin gets wet, and water on your skin makes you cooler. Water on your skin makes you no cooler. Think about it. You go into a sauna, you have water on your skin. You go into a hot tub, you got water on your skin. Do you feel cooler in a hot tub or in a sauna? No. because the temperature of the water there and the temperature of the air in a sauna is about the same as your body temperature, and you don't feel cooler at all. Just having water on your skin doesn't help. The fact that the water is evaporating, whoops, I need a green one now. The fact that the water is evaporating means it's taking what with it as it evaporates? It's taking energy with it as it evaporates. You understand that? That's a question. It's right on this worksheet right here. You're going to have to answer this in a few minutes. Recommend paying attention to this. Here's another good question. You've all made microwave popcorn, right? Everybody's opened that bag at one point or another and done what? Burned themselves. Why?
Steam is hot.
Steam is hot. That's a great answer, except that that's not the only reason you get burned. As a matter of fact, it's not even the number one reason you get burned. Look at, what's the temperature of that steam about?
A lot.
Well, what temperature does water boil at? 212. Now, if it were just boiling water, right? 212 degrees seems like it's pretty hot. And it is. What's the temperature of an oven when you cook something? 400? I could put my hand, without touching the metal, into that oven. Does it burn me as fast as that steam did? Ah, it's almost twice the temperature, and yet it didn't burn me. I could leave my hand in there to get something out. You know, I'm holding hot pads. I could have them in there for 10 seconds and not burn my hand. More than that. It doesn't burn my hand. It's 400 degrees in that oven. Why doesn't the oven burn me as much as the water does? There's actually, to be honest, several reasons. The temperature of the water, the steam that you're getting burned by, is actually higher than 212. And there are other things too. But there's one biggie that is explained by this. What does that vapor from the popcorn do when it hits your cool hand? It condenses on your skin. And when it condenses on your skin, what does it release? Energy. You are being burned in multiple ways when you get burned by steam, that you're not being burned by just hot air. That liquid water is condensing on your skin and giving off energy. So you're being burned by what's called the heat of vaporization of the liquid. And water has a high heat of vaporization, by the way. All right? All that energy is being given off to your skin. You're being burned by that, as well as another problem. The fact that the bag was closed meant that the temperature of the steam was actually higher. And we'll talk about that tomorrow. So wow, this explains a lot of stuff. It explains why you're cool. By the way, you're going to learn a little bit after I shut this off and give you a little bit of a break and have you do some other homework problems. You're going to learn a little bit. Why don't you feel so cool on a humid day? Yeah, think about it. Think about that while we're stopping here.